So what we started to learn last time was about curvilinear coordinates. And then we talked about coordinate variables like Q1, Q2, Q3, and the the unit vectors or basis vectors A1, A2, A3, right? And in general, these coordinate basis vectors are dependent on the position, right? The direction of the unit vector changes as a function of position, like in this example. And to narrow down our discussion, we assumed several properties in our coordinate system. So first of all, we assume orthogonal coordinates, which means if you take the inner product between the basis vectors, it's always 0 or 1. If two vectors are the same, it becomes 1. If two vectors are different, it should be 0. That's the orthogonal property. And then right-handed coordinate system is also assumed. So like if you take one cross product of A1 and A2, you got A3, 2, 3, you got 1, 3, 1, you got 2. Like it's kind of, this is also assumed. And we also learned about this scale factor, the concept of the scale factor. And because Q1, Q2, Q3, the coordinate variables are not necessarily be length, right? It can be angle or something else. So in order to make it into a length, you need a scale factor, h, right? And this h, of course, can also be coordinate dependent or position dependent. Like in this example, polar coordinate, two coordinate variables are r and theta. R is length by itself. So if you want to get infinitesimal length along I direction, you got dr without any scale factor. But theta is angle, so d theta is not length, right? So in order to make length, you need r, which is scale factor. And you also know that this r is position dependent, right? So if you are move away from the origin, then your r increases. So with a small change in theta, you get large distance, right? So this scale factors can depend on the position. That's another important thing. So now you know these backgrounds. Let's revisit differential operators. Okay, so differential operators is more generally written like this. So gradient is dv dl1, dv dl2, dv dl3, and again L is the infinitesimal length element along the coordinate axis. So the L is actually dl1 is h1 dq1, right? So you can just write like this. So if q1, q2, q3 were like r theta phi, then you are and then h1, h2, h3 should be determined accordingly. So that would be the definition of gradient, which is easy, not too much different. But the dependence of divergence of or curl are very complicated. If you look at this, divergence is like h1, h2, h3, 1 over h1, h2, h3, and d h2, h3, a1, dq1, h3, h1, a2, dq2, and so on. Okay, and then curl is even more complicated. You have like h1, a1, h2, a2, h3, a3, and then here in the determinant h1, a1, h2, a3. But at least you can find some pattern here, right? So now let's think how our definition of divergence and curl are that simple in Cartesian coordinate. The reason is simple. That is because h1, h2, h3 are all 1. in Cartesian coordinate because we don't need scale factor in Cartesian coordinate. So if you replace H1, H2, H3 to 1, then you can get a simple definition, like as you saw in Cartesian coordinate. If again, like H1, H2, H3 are all 1, then divergence of A is now as simple as this. Right? Very simple, like x1, x, y, z coordinate. But as I said, in general coordinate systems like spherical or cylindrical, that's not the case. So you need some, sometimes you saw like r's or thetas are randomly inside in the differential operators. So so that's the reason. So what I'm gonna do now is derive this and that from more fundamental definitions of divergence and curl. And you know what are the fundamental definitions. So by fundamental definition, I'm saying like divergence of A is limit delta V goes to 0, delta V A dot ds S, right? So this is the definition. And similarly, you know the definition for curl of A. So let's do that. The procedure itself is very similar, so you don't need to worry too much. I mean, we've done this in the previous lecture, so this time it'll be much easier. So this is divergence. And so the biggest difference between the case of Cartesian coordinate and here is that now your infinitesimal volume is not a cube, right? It has a different shape because your coordinate axes are different direction. So like in here, I would say this is your coordinate axis 1, Q1 axis, and then say this is your Q2 axis, and then this is Q3 axis. Is that right way to? No, it's the other way around. It has to be, this should be Q3 axis. Right. Can anyone know why I just flipped the direction of the Q3 axis? Yes, exactly. Yeah. As Kang Yung and Park Bom-jun said, it's due to because we just assume the right-hand rule. So if you take the inner cross product of Q1 and Q2, we need to get Q3 direction. So it has to be along this direction. Okay, now the other things are the same. So we know the definition. So what we need to do is to take this integration. And then this one, this volume, infinitesimal volume, have, of course, six spaces, right? And we want to just to try, just as an example, we want to do just two faces, which are this ABCD and EFGH. And as I said, because this is Q1 axis, right? This is Q1 axis. And then here in the middle, there's a point P, right? So the X coordinate of this guy is what? Is Q1 minus T Q1 divided by 2, right? And then X-axis, I'm sorry, yeah, I shouldn't say X-axis. The Q1 variable for this phase is Q1 plus dq1 divided by 2, right? And now you perform this integration for these two bases. And here, ds is now defined as h2, h3, dq2, dq3, a1. The reason is obvious because if you want to get a area, what you need to do is you need to multiply dl2 times dl3, right? And then dl2 is h2 dq2, and then dl3 is h3 dq3. So if you multiply this, you get this, right? And then direction of the surface is like the top surface, you have this direction, positive a1 direction. But bottom surface, you have negative a1 direction, right? And again, for a closed surface, the direction is always defined from inside to outside. So that's the direction, right? And then because S has only one component, A1 component, so and there's a dot product, you only need to take into account A1 component, right? Because there's a dot product. You don't need to worry about A2, A3 components. So it's very similar, right? Very similar to what we've done in Cartesian coordinate system. Okay, then what's different? The difference is that H2 and H3 can be position dependent, right? H2 and H3 are not like a fixed number. H2 and H3 can be position dependent, right? So H2, H3, and A1, all of these must be evaluated at this position in order to perform this integration, right? And then similarly, for the bottom surface, H2, H3, and A1 should be evaluated at this position, Q1 minus dQ1 divided by 2, Q2, Q3, right? So compared to Cartesian coordinate system, where H2 and H3 are just one and does not depend on position, this is the major difference. You have H2 and H3 that are variables. I mean that are as a function of Q1, Q2, Q3. So for the same region that we discussed earlier, this can be reduced to partial derivative along Q1 of H2, H3, A1. And in this case, we cannot take H2 and H3 out, right? Because it's like dependent on coordinate values. And then Q1, Q2, Q3. And then similar process go on. So like ACEG, like what's ACEG? Like this surface and that surface, you get this. And then the other two surface pairs, you get this, right? So if you add them up and then divide by dV, which is H1, H2, H3, right? H1, H2, H3, dQ1, dQ2, dQ3, then you ended up having this relation, right? So dQ1, dQ2, dQ3 in dV cancels out with dQ1, dQ2, dQ3 here. So just cancel out, and then you have H1, H2, H3 left, and then this equation, right? So now you understand where this H2 and H3 coming from. It's coming from, this infinitesimal surface component, and then this infinitesimal surface component depends on the position. So you cannot just simply take it out. It should be evaluated properly. So any question so far? Okay, Kang Yung asks why we have A1 vector in DS. Because we, like let's say this surface this surface is perpendicular to Q1 coordinate, right? And then we know the direction of a surface is always from inside to outside. And so we know that its direction should be this direction, which is A1, positive A1, right? And then for similar region, the EFGH, the direction is minus A1. Yeah. Let me know if this is not clear enough. Okay, so now let's move on to the curl. But before then, if you have any question regarding this, just let me know. I guess there might be, you don't have that much difficulties in understanding this because we've done this for Cartesian coordinate system, and it's not that much different, right? It's just all you need to know is that we have scale factor, and this scale factor can be position dependent, so we cannot simply take it out from the derivative. Okay, so let's do the similar thing for curl. So here also your infinitesimal surface element. So here this is your Q2 axis, and let's say this is your Q3 axis. And then if you want to evaluate the A1 component of a curl, you need to perform the line integration, like path integration for the closed loop. And here also, we're gonna just do simply do two loops. Two line segments, which are DA and BC. Okay, and because they are separated in Q3 axis, right? Q3 axis, and then this is your point of interest. So the Q3 position value for this point is what? Like Q3 minus DQ3 divided by 2, and then this is Q3 plus DQ3 divided by 2, right? These 2 points separated by DQ3 divided by 2, and then here you perform A.dl, and DL here because these line segments are aligned with A2 coordinate axis, and then DL again is H2 DQ2, right? Line segment infinitesimal length is DQ2 H2, and then here for the bottom line segment, it's aligned, it's parallel to the A2 axis, and the top one is anti-parallel. So you take positive or negative A2 for the line direction. So if you perform perform this evaluation, again, DL has only A2 component. So you only need to care about A2 component, like the 2 component of A. So if you do that, similarly, H2 should be evaluated at this specific position. So H2A2 minus H2A2 evaluated at different positions, right? So now you reduce this into differential form, right? And then here also you cannot take H2 out. And then you do the similar job for the other two line segment, and then add them up. And then you get to the conclusion like this. Okay, so what I'm saying is that, and then this can be written in determinant form like this. So from here to here, you don't need to, care too much because you just accept it. It's actually just different way of writing things. So is there anything unclear in this derivation? Because things are very similar, so I guess it's not too difficult. But at least I want to just check. How many of you understand what I just said? How many of you understand like this derivation? Please raise your hand if you understand. Okay, half of you understood, and probably the other half couldn't. Okay, so please ask questions like if you don't understand. I mean, yeah, for one thing is that I put here like optional, which means understanding this is not critical in understanding the other parts of the lecture, like electricity, magnetism, Maxwell's equations. There's no problem understanding those, even though you don't know this, you don't understand this. Okay, so in that sense, it's optional. All you need to keep in mind, which is more important, is just the geometrical interpretation of curl, divergence, and gradient and their meanings. And these, this is basically just the details, but I think it's good to know. So that's why I'm just telling this to you, but you don't need to worry too much if you don't understand this. Okay, so if there's no other question, I think I should move on. Okay, so now I'm gonna talk about the transformation between two coordinates. Okay, so let's say you have a vector A. Let's say this is your vector A. And then you have two coordinate systems. One is unprimed coordinate. The other is primed coordinate systems. So let me just schematically represent this coordinate. So let's say this is unprimed. Okay. So A1 direction, A2 direction. So you see how to decompose this. And then we can also imagine another coordinate system. Let's say like this. Let's say this is A1 prime, A2 prime. These are two different coordinate systems, right? And of course, the representation is different. So A can be represented in unprimed coordinate system or primed coordinate system, right? There are two ways. And then we want to know the transformation between those. So, let's assume that we know A1, A2, A3, and then we know of course we know this basis vectors. Then how can we obtain the value of A1 prime, for instance? How do we know what is A1 prime? So we know this, and we know this basis, how the basis vector looks like. And if you want to obtain A1 prime, what should we do? Because we know everything else, here we can use the orthogonal properties of the basis vectors. So let me tell you the trick. The trick is you multiply, take an inner product of A1 prime on both axes. Okay? If you do that, then due to the orthogonality, A1 dot A1 prime dot A2 prime is 0, A3 prime dot A1 prime is 0. So automatically this term is reduced to A1 prime dot A1 prime, which is 1. So it's just A1 prime, right? And then this upper one is A1 dot A1 prime, A2 dot A1 prime, A3 dot A1 prime. And this is A1 prime. So we got the closed form of the A1 prime with known quantities, right? And we can do the similar thing for A2 prime and A3 prime, right? So this is basically coordinate transformation. So if you represent this, okay, so you know, this is the other way around. We know A1 prime, A2 prime, A3 prime, and evaluate A1 from it. So anyway, it's the same thing. And then if you know it, then you can generalize this into a matrix like this, right? So if you just look at the first row, A1 is A1 dot A1 prime, A1 prime, A1 dot A2 prime, A2 prime, A1 dot A3 prime, A3 prime. Add them up, and that's A1, right? And similarly, the other axis you can easily interpret, right? So this is the key matrix for coordinate transformation. This tells you about like the coordinate transform. And then the elements are composed of, you can easily check the pattern here. The elements are can be obtained by inner products of two different coordinate system bases. And Im Do-hyun asks whether A1, A2, A3, and A1 prime, A2 prime, A3 prime are orthonormal basis sets. Yes, that's true. So like A1, A2, A3, A1 prime, A2 prime, A3 primes are like two independent orthonormal basis sets. That is true. And then, as I said earlier, that's kind of assumed everywhere in my lecture. Okay, so you don't. So when I say A1, A2, A3, you can just assume it. Any other question? Okay, so now we will jump to like specific coordinate systems. The beginning is Cartesian coordinate, like what we know, like XYZ coordinate. And then this XYZ coordinate, Q1, Q2, Q3, the coordinate variables are XYZ, right? And then X runs XYZ, all XYZ runs from negative infinity to positive infinity. And then unit vectors are AX, AY, AZ. That's kind of trivial thing. And what are the scale factors? What are the scale factors H1, I mean HX, HY, HG for the Cartesian coordinate? All one. Yes, exactly. We don't need scale factor for Cartesian coordinates. So it's all one, right? So if you want to evaluate the infinitesimal volume element, it's just dx, dy, dz. Simple enough, right? And now let's move on to cylindrical coordinates. Cylindrical coordinates, the coordinate variables are rho, phi, z. By the way, in this lecture, I'm gonna use this convention for the cylindrical coordinates variables. So I understand that some people want to use like r, theta, z, or whatever, like you know, whatever symbol for cylindrical coordinates. but I, at least in this lecture, let's use these symbols for cylindrical coordinates. So rho, phi, z. Rho is the distance from the z-axis, okay? And then phi is what we call azimuthal angle, right? So angle in like xy plane. And then z is z, the same as the Cartesian coordinate. And then if you think about the range, the domain of variables, rho runs from 0 to infinity, right? There's no negative value. Well, we can define negative value, but it's anyway. That. And then phi is 0 to 2 pi, right? 0 to 2 pi. And then from then on, it's just the same. And then z runs from minus negative to positive negative. Negative infinity to positive infinity. And unit vectors are a rho, a phi, a z, like in this figure. And then, as I said, the direction of a rho and a phi depends on position. So if you evaluate, let's say, what's the direction of a rho at this point? It's here along y-axis. What's the a rho in that point? At that point, it's just along x direction. So it's dependent on position. Now, the scale factors. What are the scale factors? H1, H2, H3 for this case? Can anyone answer? What's H1, H2, H3? The scale factors for the cylindrical coordinates. Anybody? Cylindrical, the scale factors for the, right. Okay, thank you, Kang Yung. Yeah, by the way, yeah, well, you have many different ways of writing rho. Kang Yung wrote in Korean, and then, yeah, but Sehun said RO, but it's actually RHO, right? RHO is how to write rho. Anyway, yeah, so 1 rho 1, that's the case. So the scale factors, rho and z is already length. You don't need scale factor, but phi is angle, so you need scale factor, which is rho. So dv, the infinitesimal volume element, is rho, d rho, d phi, dz, right? It's easy. Now let's see how the differential operators looks like in cylindrical coordinate. So it looks like this. Gradient is not too complicated, right? Because you have a scale factor only for phi. Only phi component is different, right? And then if you look at the divergence and curl, you can see that there is a rho inside here, rho outside there, and then here there's the 1 over rho, and then there's nothing, right? So if you saw this without knowing this, it would look really random, right? So now you know this, and then okay, so H1 and H3 are 1, and only H2 is rho. So let's put H2 rho, then everything is plain, right? And then you know why this is the case. You even derived it. But if you just looking at this just for the first time without any basis knowledge, then this look pretty random. Sometimes there's rho here, sometimes there's nothing. Sometimes there's a denominator, sometimes there's nothing. So it's very complicated. And similar here, it's like, I think it's difficult to memorize. And that's why I try to explain why this is the case, like using generalized coordinate systems. Okay, now let's talk about coordinate transformation. So in order to transform coordinates, we need to do two jobs. One is transformation of coordinate variables. And the second is the transformation of basis, which I mentioned earlier. So coordinate variable first. Let's say we want to write x, y, z, and then cylindrical coordinate rho, phi, z. So if we write rho, phi, and z as function of Cartesian coordinate variable, what's rho? I guess this is easy enough, right? Rho is square root of x squared plus y squared, right? And then phi is tangent or arctangent y over x. And then z is g, right? So this is coordinate variable transformation because they use different coordinate variables. You need to first transform this. And then you know the other way around. Let's say, what's x in terms of rho, phi, z? Can anyone answer? Like, what's x in terms of rho, phi, z? Can anyone type in like x and in terms of rho, phi, z? Right, rho cosine phi, right? Good, thank you. So it's rho cosine phi. And then y is rho sine phi. Everyone knows this. So this is about transformation between coordinate variables, but this is not the end of story because we need, so this is just a rho theta phi and x, y, z. But the thing is, we have also like ax, ay, az, and a rho, a phi, and az. So we need transformation between these two, right? So here's the transformation. And as I said earlier, the basis transformations can be written as a matrix. And the matrix components are the inner products of basis vectors, right? And so let's look at it a little more carefully. So like z coordinates are just shared, right? So it's just one, right? az is equal to az. And then because of that, because z is perpendicular to rho and phi, it's all 0, right? So that's trivial. And then if you think about a rho and ax, so this is a rho direction, and then this is ax direction, and the angle between these is phi, right? So if you take the inner product, it's cosine phi. So all you need to do, like, because a rho and ax and every a's are actually unit vectors. So all you need to figure out is what's the angle between these basis vectors. And then you take a cosine, that's it, right? So then somebody would ask then, okay, so here then why there's a sign? Well, that is because it's kind of cosine, I don't know, pi over 2 minus phi or something like this. I mean, this can be reduced to sine, right? So all you need to do again is figuring out the angle between the basis vectors. Then this is done. Okay, so keep in mind there are two things. One is transformation in coordinate variables, and the second is the change of basis. So you need to do both in order to finish your complete your coordinate transformation. So here's the question. You have vector A represented in Cartesian coordinate. The question is, find the representation of same vector in cylindrical coordinate. So you have 3 minutes. Please work on this problem. Okay, time is up. So how many of you got the answer? Please raise your hand. How many of you got the answer? Please raise your hand. Raise your hand, please, if you solve the problem. Thank you. Okay, about half. For those who hasn't got the answer, can you tell me what was the problem? Is that like is it because time was too short, or you can just type in like why it was difficult for you to get the problem. If it's about the time, there's no problem. But if you like don't understand anything, you'd better ask questions to understand this. Okay, so let's do it together for this problem because it's the first one. So now so again, the first thing is to do the the coordinate transformation. I'm sorry, coordinate variable transformation. So we can change this into, so x squared plus y squared is just a row, right? And then here it's rho squared z squared ax minus yz is what? Rho sine phi z az, and then rho squared z squared, right? So is that it? Is that the solution? No, right? Because we still have ax and az. It's still in xyz coordinate. So in order to finish the coordinate transformation, we need to go to a rho, a phi, az coordinate systems. And in order to do that, we need to do this matrix equation, right? We need to multiply this rotation matrix. And then that process is given by this. So first, you, as I said, first you change things into rho phi z, but maintaining ax and az. And then second, you change xyz to rho phi z basis using this basis transformation, right? And then in this position, in ax position, you have this value, and then az position, you have that value, and then ay position you got 0, and then you apply insert that, and then perform this matrix equation, and then you get the solution, right? And then this is the representation of A in cylindrical coordinate. And this applies to all coordinate transformation. So you need to know variable change and then basis change, right? Hope this is clear enough. If it's not, please ask questions. Okay, you can just type in the question. So I'll move on. But if you have a question, you can keep typing in, and I'll come back and answer those questions. So now spherical coordinates. Spherical coordinates, we have r theta phi. Okay. So again, just let's stick to my way of using symbols. Okay. So r is the distance from the origin, r. Phi is azimuthal angle, same as the cylindrical coordinate. Theta is called polar coordinate, the angle from with respect to the z-axis. So this is called polar coordinate. So r runs from 0 to infinity. Theta runs from 0 to pi. Okay, so 0 to pi. And then phi runs from 0 to 2 pi. And here, what are the scale factors? Can you answer that question? Like, what are the scale factors for r theta phi. You know the scale factor for, okay, yeah, what are the scale factors like r theta phi? So please type in if you have it, if you know the answer. What's the scale factors? So scale factor for r is just 1, right? It doesn't require any scale factor because r is already length. But what about the other two? Okay, so there's interesting opinion like one r, and some another people say like another one say 1 r sine theta. Yeah, so, and many people say 1 r sine theta. So let's see how things are gonna go. Like if you, so here you have 3 components. So this one is your dr component, and this one, I'm sorry, this one is your d say dl2 component, and then this is your dl3 components, right? And then dl2 is just r multiplied by d theta. So the scale factor for theta direction is r. Next, and then scale factor for L3 direction, you need to do a projection. Okay, so projection to the bottom, and then at the bottom, if you do the projection like a vertical projection, you can see that the length of this is r sine theta, right? And then you have d phi, so you have r sine theta d phi, which is your length, infinitesimal length component. So r sine theta is your scale factor for this case. Okay, so like here, h r h theta h phi, or 1 r r sine theta, and then of course dv is r squared sine theta dr d theta d phi, right? And now in spherical coordinate, the differential operator looks even more complicated, right? So here's r squared sine theta, r sine theta, r sine theta here without anything inside. So this looks also pretty random, right? If you just look at it. But if you know what are the scale factor and how it's working, then you understand this. Okay, and then here too, curl can be defined like this. The same, because it's the same, I'm not gonna go into details. And this is an exercise about the spherical coordinate integration, but I'll just give you the answer. So what this tells you is that here, check the divergence theorem. So divergence theorem is like the surface integration of a volume is equal to the divergence of A, the volume integration of divergence of A. So to check the divergence theorem, you need to evaluate the surface integration and volume integration separately, and then compare and see if they're actually the same. So, and then because definition of A. Definition of A is AR, right? So you can evaluate, you have DS vector, and then you have, A. So you can just, apply these definitions in order to get the solution. And similarly here, the divergence of A, you can obtain based on the formula that is given in front. And then you just, and then it's, fortunately, divergence of A is actually 3 in this problem. So just this integration is very easy. 3 times the volume integration. And you know the volume of this thing. So it's 3 times this value, right? So what that means is that the 3 times the volume of the outer sphere minus the inner sphere. So then you get this. And then this integration is a little more complicated, but it's not that more complicated. And then if you evaluate that integration, you will see that they are actually the same. And yeah, and I think this is kind of straightforward problem. So I don't want to spend time, just giving you time to solve this problem. But if you have any question, you can always ask. If anything is unclear, you can always ask questions. So the rest of the lecture is about just the coordinate transformations, like Cartesian to spherical, and spherical to cylindrical. I mean, those things. So let's do Cartesian to spherical. Let's just do a few things. So let's say you have, say, x, y, and z, and then you want to write it using r, theta, phi. Then, because this is r, right? Your z-axis, z coordinate is r cosine theta, right? And then your y coordinate is, you first need to project this onto the xy plane, which is r sine theta, and then take cosine of it. So r sine theta cosine phi is x component, and r sine theta sine phi gives you y component. I think you've done this many times, so I'm just being very brief in talking about this, but just want to, I just want to make sure. You've done this before, right? How many of you, see this for the first time? Can you raise your hand? For those who saw this XYZ to R theta phi transformation for the first time, raise your hand. Okay, so everyone knows it, right? Everyone knows this beforehand. So I don't want to spend time on it. Like everyone knows it, so it's kind of easy thing, right? So R theta phi to XYZ, and then change of basis, the same. Like you have r theta phi to xyz, or the other way around. All you need to do is to figure out what's the angle between the two, and then if the angle calculation is difficult, then you need to check this geometrical kind of layout, and then figure out what are these components. Okay, so you can do that. And then finally, you have cylindrical to spherical coordinate systems. And this is even easier, right? If you look at this, in this case, these two coordinate systems shares one coordinate variable, which is phi. So phi is phi. And then r and rho z is having this equation, like r and like, okay, this is not r, this is rho. Rho and z, so rho squared plus z squared gives you r. So I think it's pretty straightforward, right? And you've done this many times, so I don't want to spend too much time. So finally, coordinate transformation between cylindrical to spherical. So let's say you have next. Yeah, so let's say you have a rho, a theta, I'm sorry, a phi, a z, And then you have a matrix, and then a r, a theta, a phi, r theta phi. Now, which component is 1? Can anyone know which component is 1? Like among these 8 component, which one should be 1? You can just type in the index. Right. This guy, right? This guy must be 1, right? Because it connects this and that, which are the same thing. And then automatically this becomes zeros, right? Because a theta, a phi is just a phi, and then there shouldn't be any AR or a phi, a theta component. So it becomes 0, and then 0 here too. And leftover is the other 2. The other 2, of course, is just sine phi, sine whatever. You can obtain, right? If you look into this carefully, then you can figure out what are the components. So if you look at the answer, that is true. Actually, 0, 0, 1, 0, 0, and then there's the sines and cosines, right? But the essential thing is, again, like you figure out like what's the basis transformation. So I'll leave this exercise for your homework. I mean, you don't need to submit this exercise, but you can just do it by yourself. It's not that difficult. I mean, the process is exactly the same, right? First, you want to transform the variables from x, y, z to r theta phi. And then you want to transform the basis using this matrix. Same procedure. So this is it. This is it for the mathematics review.